So while we use simulated parameters and bootstrap samples to assess primarily the uncertainty around quantities where we do not immediately have a good assessment of this uncertainty, Monte Carlo is used more to evaluate how well a particular statistical model or test is working. In particular, we often have cases where we know that the asymptotic properties of an estimator are good. We know that it is a consistent estimator, but we also know that it is biased in a fixed size sample, in a finite size sample. And the question often is how biased is it? Or how do different estimators compare on a finite sample in terms of the accuracy of the estimates? And this is often difficult to assess analytically. We can often mathematically prove consistency. We can prove that as the sample size increases, it converges on the true value, but it is difficult to mathematically prove how quickly it does so. And so it's difficult to know for a given sample size how accurate these estimators are. So in a Monte Carlo study, we generate fake data. We generate fake data because then we know at the moment we generate the data what the true parameters are. So remember that statistical models is about estimating parameters, population values, based on statistics, for example, regression coefficients. If we have an artificial data set where the data is generated with the model specification that we have in mind to test, then we know the true parameters. And then we can estimate a model and see how well the estimated model matches on the true parameters. So the data generation process refers to creating these fake data sets where we know the underlying statistical model, and then we estimate the statistical model on this fake data, and we do this many times. This is where the simulation comes in, and then we can see how well on average this estimator performs in trying to reveal the original parameters that we put in. So the next few slides show a simple example of this using a linear regression. So here's the data generating process for a assumed linear regression. So remember that in the linear model we typically have an intercept, in this case 0, and we have a slope coefficient, in this case 3, and we have an error distribution that follows a normal distribution that has a mean of 0 and some variance, in this case 1. We also need to generate fake data for x, and in this case we assume a normal distribution with a mean of 5 and a variance of 2. So this is the data generation process. This is the data that goes in when we create our artificial data sets many times. So here we create 1,000 fake data sets, each with a sample size of 50. So each time we randomly sample x, we randomly sample the errors, and then we calculate y. And so we have 1,000 different sets of x and y, and we can then run regressions on those to see how well they do in recovering the fact that the intercept was 0 and the regression coefficient 3. So we simply add the estimation, and we then also need to save, of course, the results. So with the lm command we can estimate the coefficients. With the coef command we can extract these coefficients, and then we save them in this estimates vector. So in this case we already assume that the intercept is 0, we only estimate the beta, and then we get lots of estimates for the slope coefficient. And then you can evaluate the efficiency by plotting or looking at standard deviation of the estimates. You can see how much it varies across the true value. You can look at the bias, so you can look at how much on average these estimates deviate from 3, which was the true value. Or we can look at the mean square error, which is a balance between efficiency and bias, by looking at the variance and the squared mean average distance from the true value. All of this gives you a sense of how well this estimator works in trying to estimate the original slope coefficients, which you know is 3, but we have now 1,000 different estimates based on 1,000 fake data sets for a sample size of 50.